This is Lab 5, Choose Your Own Adventure, and I chose to model friction. The goals of this lab were to examine the motion of a ball rolling across carpet and to determine the coefficient of friction for the system by using Newton's second law. The result was the predicted motion with the computational model closely matched the actual model, and in the end I determined that the coefficient of kinetic friction was about 0.07. We start from a fundamental principle for this lab. We know that net force is equal to mass times acceleration. However, the net force is not zero because the ball is accelerating since it's slowing down. The initial velocity is not equal to the final velocity since the final velocity is zero when it reaches a complete stop, but the ball has an initial speed. Kinetic friction is essential for this lab because it is the force that is opposing the ball's motion. Kinetic friction is equal to the coefficient of kinetic friction times the normal force, and we know that normal force is equal to mass times acceleration due to gravity. We can ignore sag friction because it is zero in this case, since the ball is moving. The net force in the x direction is just equal to the force of kinetic friction. So to accurately model the ball's motion, we have to look at the forces acting on the ball. We have the force of gravity and the normal force and the force of kinetic friction. Even though it shows it here, we are not going to look at the force applied on the ball because we're only examining the ball's motion after there is no longer contact between my hand and the ball. So the force of gravity is the weight of the ball. The normal force is just equal and opposite to the force of gravity. Then we have kinetic friction, and the net force is just the sum of all the forces, so the force of gravity, the normal force, and the force of kinetic friction. We have to also update velocity, and we also have to update the ball's position since it is moving and the velocity is changing. We also have to initialize several things, such as the ball's mass. We set it equal to 0.26 kilograms, and we started the ball's position at the origin. The ball's initial velocity is about negative 1.0238, which I determined from tracker, and we started the time to be 0. I also changed the time duration to be 1.25 seconds because this is how long the clip was I examined in tracker. Okay, so the next step was to find the coefficient of kinetic friction. I did this by running my computational model several times so that way the final position, x position, of the ball would match the final x position of the actual model that I found through tracker. So in the end, they match up, and I found that the coefficient of kinetic friction to be about 0.07. So here are the results of the computational model. The blue arrow represents the force of kinetic friction, and it decreases as the ball moves, and it's slowing down, which makes sense because when the ball is motionless, it has no kinetic friction and only static friction. Likewise, it doesn't have any static friction when it's moving and only kinetic friction. Here's the graph, which shows that initially the ball does have a velocity and eventually slows down to a complete stop because of kinetic friction. So here I made a graphical representation in order to compare the actual model to the computational model. And you can see that there are minimal differences between the two, meaning that the computational model does in fact accurately predict the actual model's motion. The first what does it mean question asks which objects exert forces on the block with non-zero y components. The surface and the earth would exert forces in the y direction and they cancel each other out. And the net force in the y direction is zero because the ball is not moving in the y direction. It's only moving in the x direction and it's only accelerating in the x direction. So which objects exert significant forces on the block with non-zero x components? So that would obviously be the carpet. The carpet is what is causing the kinetic friction and causing it to accelerate and come to a complete stop. So since we've already studied the energy principle, the next what does it mean question asks, does this model obey the energy principle, and if so, where does all this energy go? So we know the change in energy is equal to work plus a change in heat. There's no work done, but there is a change in heat. So it may seem that energy is being lost from the system since the ball is slowing down and therefore losing kinetic energy, but really it's just transformed into a different form, which is heat. It may not be noticeable to us, but the carpet in fact is heating up. The next question is a what if question asking, imagine the ball is rolled on a frictionless surface without any other forces opposing its motion. How would its motion change? Since there's no force opposing its motion, it would just remain moving with a constant velocity, and therefore, in this perfect system, the ball would never slow down. So, in conclusion, we were able to predict the ball's motion with a computational model, and the ball does in fact come to a stop. So, it does not move with constant velocity, and the net force is not zero. The force opposing its motion is due to kinetic friction.